Hello, and welcome to Chapter 3 of Physics with Calculus for Aquinas University. We're covering the OpenStax University Physics course, as you all, I hope, are well aware by now. And today I'm going to go over Chapter 3, Motion Along a Straight Line. Friendly reminder, as I do always for these lectures, I'm going to go through the broad concepts and a few selected examples to help you understand some of what I'm trying to teach you in this chapter. However, this lecture is not meant to be the only exclusive thing that helps you through the process. You have access to the book, you have access to the slideshow, you have access to, well, anything on the internet that'll help you figure this stuff out. Talk to your classmates, talk to your tutor, utilize all your resources to get things accomplished. With that being said, I'm also going to go back and forth between the book and the slideshow in order to convey my points. And let's begin. So, motion along a straight line. We're talking physics and we're talking calculus here. So everything's going to be slightly different looking than maybe when you originally learned these topics in, say, high school physics. When we're using more or less the same equations, we're going to be drawing them, writing them from a calculus perspective. So that's going to be our main thing I want to try to get across here. Motion in a uniform or straight line, of course, is otherwise known as change in position or displacement. And then if you displace things over time, you have a velocity. And if you change your velocity over time, you have an acceleration. And that is the whole point. That is what we're doing here in this example shown here. Again, hopefully this notation is familiar to you, that triangle X is delta X or change in X. XF is final position of X. X0, X naught, as I call it, is initial position of X. So the teacher moves to the right. Convention dictates that in the X direction, right is positive, and in the Y direction, up is positive. And we show these things mathematically as well as graphically in this page, but throughout the text, and when you kind of use these tools after this class, mathematically, the formula is going to be what you do. So make sure you understand the language of the math that's being shown here. As you move back and forth, right? This is a question of the book I'm skipping because I want to do a different one. But Jill's movement back and forth from her house, going wherever she happens to be going, can be tracked mathematically, and you can determine overall how far she moved, how long it took her, all these other things by using the equations. Again, I'm not going over this particular example. I've got another one I want to do, but this stuff has a math to it, and this stuff has a graph to it, right? Graphically, we can describe Jill's position as such, with minutes on the X and position on the Y. If she moves away from her home, we can consider that move to be the positive X direction because she's moving to the right. So we graph it as a bump up. That first triangle is that first leg of that first triangle there, going from 0 to 0.5, is that first arrow on the top. Then she walks back home. She comes back to her rest position of 0, right? This one, same song and dance, just you have a bicyclist going around. But where this lands itself into calculus is we're not just looking at these as pure equations or graphs. We can derive more detailed information out of it. Go back to your calculus conversations. What is a derivative? It's the slope of the line, right? So, and knowing the slope at any given point of a line tells you what it's doing and can provide very valuable information. So we're not zooming into a pinpoint at this time yet, but we will get there eventually. So if you look at a position versus time graph, the black arc there, and then choose any two position points and compare them, you will get a velocity based off of that comparison. Velocity, of course, is distance divided by time, right? Miles per hour. So if we were taking the position measurements and the time measurements and seeing the difference, we therefore get a velocity. That's what's going on in the equation down in the text below. And hopefully you can make a connection between those differently colored arrows the slope of them, and the velocity. And, preview for later, how are we going from distance and time to velocity in a calculus perspective? Again, same song and dance. Just now we're dealing with the bicycle, I guess. What fun. Velocity can be graphed in the same way as position, of course. Anything can be graphed if you really want it to be. In this example, we have a velocity of 1, then a velocity of 0, then a velocity of negative 0.5. What's happening here? Well, the first part of the trip, the object is, whoever this graph is about, is moving, right? So a positive velocity is moving in the positive direction. The positive direction would be the lower part, for example, right? Whatever you describe as a positive direction, moving in that direction is a 1 on the scale. And then what is a 0 velocity? That's not moving. And a negative velocity moving in the opposite direction of the positive velocity. And then the scalar product of that, a velocity of 1 meter per second is twice the velocity of 0.5 meters per second. Hopefully these are things that are more refreshers for you than in depth. If this is not something that's like clicking, let me know, let your classmates know, let your tutor know. We'll try to catch you up a bit. So let's go to the textbook and do an example question. Example 3.4. Again, this is from the University Physics Volume 1 textbook on OpenStax. So you'll have access to this. Everyone does. It's a free textbook. Determine instantaneous velocity versus speed. So let's consider a particle. Let's consider the motion of a particle in which the position is x of t equals 3 meters per second multiplied by t of course being time, x being position, minus 3 meters per second squared. So meters per second is a velocity. What is meters per second squared? That's an acceleration, right? Times t squared. So use this information. Can you figure out the instantaneous velocity at 3 set time intervals? And can figure out the speed of the particle at these time intervals. So how do we figure that stuff out? Well, again, this is something where the non-calculus side of this and the calculus side of this are the same idea, just the calculus side uses calculus writing for it, right? So we know that velocity is distance over time. So we're going to write the stuff out as v of t. I say v of t because the of is the parentheses, right? Hopefully this language is familiar to you, is equal to dx of t over dt. So the displacement in relation to t divided by t. That gives us our velocity by definition. And we know, again, right? We know that the distance is given to us by the equation x of t shown above. So we take that information and then we can rearrange our equation down here, the v of t equals dx of t over dt. And we can solve it for t because t is the question that we're trying to solve here, right? We're trying to solve time at these separate intervals. Cool. Makes sense. So as you can see from the solution A, separate the equations out, and we find that at any particular time, for example, 0.25 seconds, when we plug in 0.25 for t for these examples, we get 1.5 meters per second. So given that position change shown in the equation, at a quarter of a second after you start counting, you're going 1.5 meters per second. And of course, you can plug the information in for 0.5 and for 1. And what's fun about this is since the equation has a negative sign in it, the longer you go, you start going forward and you start going backwards, right? So a negative 3 meters per second at 1 second means you're going in the opposite directions you started in. So you're doing, where's that graph at? Well, there. We got the graphs on here, right? Your velocity is changing according to the graph. You are backing up, slowing down, something like that. You can derive from this however you wish. But that's how that math works. Speed, of course, is the I don't care about direction version of velocity. So speed is the absolute value of the velocity. Just take the absolute value of those 3 numbers to get your answer, right? We have a graph on the slideshow here, again, showing the 3 steps that we had and what they mean. And the original displacement equation, of course, has a squared in it, so you have an arc to it. boom. But then when you calculate the other things out, you land yourself on a straight line showing that change, right? Again, the equation isn't like difficult. It's just understanding what's going on here from a writing it in calc language point of view. The math is not difficult at all. It's division, multiplication, actually. Cool. So again, we have other examples from the book of the real world using these things accelerating and slowing down and stuff like that. Here you have a train going against, gravity and stuff like that, or braking, how all that plays out. Engineers, of course, need to care a lot about this process. If the train is told to brake too late and smashes into something on the rail system, that's a fired engineer. That's a very bad job. So you want to avoid that, obviously. Cool. We can, of course, incorporate acceleration in this. That's the gradual change, snapshot to snapshot of the velocity. And acceleration dictates how it changes. Hitting the gas pedal is accelerating. Hitting the brake is accelerating in the negative direction or decelerating. So, because if you ask questions, story problems, right, you need to translate the words into the math. And remember, a negative is just what's going on, but in the other direction. So let's jump ahead here. Again, these are questions from the text. I do not go over every question because I don't feel that's necessary. And I kind of want you to look at the book too. The book is very well written to be easy to go through. So all your equations, of course, are in the book. I'm not proctoring your homework and stuff. So just have all your equations there in front of you. It's what professionals do anyways, right? And go through exactly what's going on here. So I am trying to get to, where's my next, there it is. Okay, good. This image is the same as before. You can take slopes of various things, acceleration. Acceleration, velocity, and displacement are all like derivatives of each other, right? Takes the derivative of an acceleration equation, you get velocity. Takes the derivative of a velocity equation, you get displacement, x. I'm not going to go over that a lot in this particular chapter. In this particular lecture. Again, I'm making the assumption that since you came to the physics with calculus class, you know what a derivative is. But graphically, the stuff's all going down. Doesn't matter what's happening with the velocity. If it's decreasing or increasing, you can still take all these measurements the exact same. Right? Cool. Example 3.6. Let's go through that one. So here we have some graphs relating to this question. A particle is in motion and is accelerating. The functional form of the velocity, the equation describing what's going on, is shown here. The velocity with respect to t is equal to 20 meters per second squared times t minus 20 meters per second times t minus 5 meters per second squared times t squared. So the thing is in motion and it's decelerating, right? It has a negative velocity, so it's braking. So given that information, find the functional form of the acceleration. What's acceleration looking like? Tell me the velocity and acceleration at specific time intervals and interpret what you're saying there. Cool. So functional form, what is acceleration? Well, in the way that velocity is displacement over time, acceleration is velocity over time. They're interconnected, right? So if we take the velocity equation and we divide it by time, we get something that cares about the acceleration. In this case here, 20 meters per second minus 10 meters cubed over t. Cool. Easy enough. But how do we use that information? What can we find out useful byproducts given what we just talked about here? Yes, we very much can. If we take our velocity, and I want to say these equations are shown in the book, right here. So if you're looking at this, you're like, I don't get what's going on here. Scroll up a little bit in the textbook, right? these questions will be shown to you and the equations will be shown to you. I think, does the book even directly reference the equation? Sometimes the questions even directly reference the equation if you keep reading around. Hey, there it is. Equation 3.9. Sweet. So what do we do once we have the velocity and the acceleration forms of the equations? We plug and chug in our numbers, right? The book doesn't show you how to do the math because the math should be apparent to you. Put t equals 1 in for the velocity, find out the instantaneous velocity. Put t equals 2 in for the acceleration, find out the acceleration at 2. Cool. However, so we get these nice pretty graphs out of this showing the changes in the velocity due to the acceleration and the slope of the instantaneous pinpointed second marker is the acceleration. So you have positive acceleration at 1, 0 acceleration at 2, and negative acceleration at 3, and it continues to peter out, right? And at 5, you have this kind of this very similar acceleration to 0.3, but your velocity is much, much lower. Acceleration is, of course, a straight line because velocity is the derivative of the acceleration. Cool. And the acceleration is constant because, well, that's what the equation says. The acceleration is constant, right? Negative 5 meters per second squared. Again, what I'm trying to emphasize with these lectures is that the math we're doing is not super complicated here. Find the equation, make sure the equation matches. The easiest way to know that you found the correct equation is if you write down your knowns and then find something that solves for your unknowns. We've talked about that quite a bit in our lectures, and it is vital. If you get lost, if you don't quite know what you're supposed to do, take a second, take a breath, scroll back up in the textbook, scroll back up in the slideshow, and try to find something that matches. You don't need to memorize this stuff. I'm not asking you to memorize all these equations. All right, so what do we have here? Different types of acceleration, graphs of an instantaneous acceleration versus time for two different one-dimensional motions. This is kind of referring to the interplay between these various different things. On the left here, we have a graph showing the acceleration kind of bobbing around a bit, right? And on the right, you have snapshots of the velocity in relation to the way the acceleration is moving. And that's rehashing that top graph there, right? Any given spot, you can determine the acceleration by the velocity, and at any given spot, you can determine where the velocity is going by the acceleration. That's how these stacked equations, the derivatives and stuff like that work. I'm not going to put a whole lot of effort into graphical analysis for this class. I personally don't think it's super relevant. The majority of the time, especially now that we have MATLAB and R and stuff like that, that will easily create all this stuff for you. The old pen and paper is a good baseline tool, but I'm not going to stress that stuff very much. Example from the text regarding acceleration, how that plays in. I'm not doing that one. I'm doing this one because I like dragsters. I used to be an NHRA fan. So we're going to go with Tony Schumacher in his example, 3.8. I want to say that's on the next chapter. Yes. Cool. So again, I'm going to scroll past this stuff, but all the equations you need to answer the questions from this chapter are in the chapter. And they're worked out. Here's the one I skipped about the airplane because I want to go down to the dragster. So I tell you that dragsters can achieve an average acceleration of 26 meters per second squared, which is a lot. And then I also say to you, suppose the dragster accelerates from rest at this rate for 5.6 seconds. How far does it travel? How far does a dragster go in 5.56 seconds, given that set acceleration? So think about this. What do we have? What do we need? What do we want? Well, we're given a lot of knowns, but we're not given the variables associated with them. So you have to extract the useful information out of those three sentences. For example, dragster can achieve an average acceleration of 26 meters per second squared. So we have an average acceleration given to us, an A, right? and it accelerates from rest. So you have a v naught of 0 and an x naught of 0 at this rate for 5.56 seconds. Good. That's a t equals 5.56. How far does it travel? Well, that's an xf, right? That's a displacement. So we want to know a xf, a final location, given an acceleration, given a starting point, and given a time. And technically given a starting velocity because it starts at rest. So can we find an equation that gives all this stuff? Well, yes, we can. Scroll back up, go through your physics equations, bam, right there in front of you. I think actually there's a section of the book that's all just the equations, I want to say. Maybe it wasn't in the index. I can't quite remember. Mathematical formulas down here, appendix E, right? Use this stuff. I'm not going to stop you. I want you to. So let's use that equation, plug in what we know, solve for what we don't. That's how math works. All right. So first, again, identify knowns and unknowns. Look at our equation. Remove the things I don't care about. So since the starting position and the starting velocity are 0, we can plug zeros in those equations and not care about them. So our final position, our xf, is simply 1/2 times our acceleration times our time squared. There you go, right? That seems like it might have been a big question, but when you take the time to write down your knowns and look at your equations, you can usually find that the answer is pretty straightforward. The dragster covers 402 meters in 5.5 seconds. That's a lot, by the way, just so you know. We're hitting, about half a kilometer, almost half a kilometer in 5 seconds. These things go pretty fast. So again, more examples from the text. If you want, pause the video, go try to do these text questions on your own. You will find it's reiterations using different equations of the same concept. All right, so let's go to question 311 next. See, again, new equations. Cool. How to use them. Examples. Big stack of equations right there. Screenshot that, write them down on your piece of paper, have those handy for when you're doing this work. There's the one I'm skipping because I want to do 311. Suppose a car merges into freeway traffic on a 200-meter long ramp. So starts the ramp, x equals 0, x naught equals 0, ends the ramp, xf equals 200 meters. If its initial velocity is 10 meters per second, so it does not start with a velocity of 0, v naught is 10, and accelerates at 2 meters per second squared. So I'm given from that information, I'm assuming the average acceleration, not a variable acceleration. How long does it take the car to travel the 200 meters up the ramp? So how long does it take to get there, given where you start and where you end? And what do we need to know? Well, we need to know time and velocity. Is another thing we don't know. So we can track down our knowns. The sketch here, I don't know if it's super useful, but writing down your knowns in the way that's shown here in this sketch is what I'm going to suggest you do. It's showing your work, right? So identify your knowns, find an equation that might fit things. We have this equation here, x equals x naught plus v naught t plus 1/2 at squared. And given some of our knowns, such as x naught, v naught, x, and a, we can probably solve for some of our unknowns. In this example, in that equation, the only unknown is t, right? So we can fill it all in and rearrange and solve for t. The reason I want to do this equation is because I wanted to remind you of something. When you get to your final equation, you have a t and a t squared. And you can rearrange equations into x squared plus ax plus b, I believe. And that is the quadratic formula, right? Think way back. That's probably going a bit back in high school, right? The quadratic formula has a known equation that solves for it. Negative b plus or minus square root of b squared minus 4ac over 2a. Every math teacher has this memorized, right? Don't get lost when you see squareds and stuff like that. Remember, there's equations, there are examples, and you can punch this stuff in. So when you solve for the quadratic formula of this, you're of course given two answers, right? A plus and a minus. T equals 10 and T equals negative 20. Well, it didn't take negative 20 seconds to drive up the freeway ramp, right? So it must have taken 10 seconds. There you go. There's your answer. Again, the math wasn't necessarily difficult, but it's important to slow down and catch all of your equations to realize what needs to be done and how to do it. Other examples from the text that I suggest you go through if you need the work. If what I'm saying, you're like, oh yeah, that's nothing. I get this stuff. Sweet. Chapter 3 is easy for you. But if you're looking at things, you're like, where is he getting this? I think I need to do a couple examples. There's plenty of examples in the text for you. Or elsewhere, whatever you want. One of the last chapters we cover is gravity. Gravity essentially is a given acceleration for any particular problem. That's how you treat this stuff. Classic, of course, is dropping the ball out of a window. You guys probably did like the egg drop experiment in high school and stuff like that, where given a known acceleration of gravity, you can dictate how fast something is going. The more something falls, the faster it gets, right? Because gravity is an acceleration, and it tends to be in the negative direction. Let's do a classic example, 3.15, a pop fly in baseball. So here we go. Batter hits a baseball straight up at home plate, and the ball is caught 5 seconds after it is struck. Hopefully this picture really helps explain that. What is the initial velocity of the ball? What's the maximum height the ball reaches? How long does it take the ball to reach its maximum height, its apex, right? What's the ball's acceleration at the top of its path? And what is the velocity of the ball when it is caught? So some of this is math, some of this is rationalizing. Okay. For example, what is the acceleration at the top of its path? Well, think about that. What is accelerating the ball, right? Is the ball undergoing acceleration if it's at the top of its apex? So what do we know? What don't we know? Well, I know a initial displacement and I know a final displacement, as shown here. They're both 0, right? I'm assuming, I guess the batter and the catcher are the same height. And we know a T initial, a TI, and a TF or T final, 0 and 5. And that's all we're given. But again, this is in the chapter free fall, so we have gravity. We know the acceleration given to the ball. We know the acceleration is 9.8 meters per second, or gravity, G, 9.81. Sometimes you use 9.81, stuff like that. The equations given in this chapter always have a negative sign in front of the gravity. Well, okay, let me restart that sentence, actually. Gravity is always negative in standard convention because the positive y is up, negative y is down. Gravity always pulls you down, therefore gravity is negative. Equations sometimes will auto include a negative in front of gravity, is the subtraction symbol in front of the 1/2 there. So you don't have to think about it. But if you're dealing something with gravity, make sure that gravity is decelerating, as gravity is in its correct direction when you're doing your math. If you have gravity speeding something up as it goes up, that's not gravity, right? So given all the information we had, can we find an equation that gives us some useful information? Well, this equation here, y equals y naught plus v naught t minus 1/2 gt squared, does in fact give us useful information because we know y naught, right? We know y, we know where it ends, the entire arcing of it ends, and we know the time, and we know gravity. So this gives us an opportunity to look at v naught and say, okay, can that tell us something useful? And in fact, it can. So we can solve out and find a velocity of 24.5 meters per second. And I can see you wondering, well, how do I know it's counting going up and going down? Well, you know it's counting going up and going down because that last t is squared, right? It has a parabolic, the graph is parabolic. So this question specifically answers exactly what we're asking, travel time up and down. And once you know your initial velocity, you can look at other equations, such as v squared equals v naught squared minus 2g in parentheses y minus y naught, to solve other problems. For example, as shown here, if we assume our starting initial y naught and we have that y be the apex or the top of the pop fly, as opposed to the part A where we assumed y was when it was caught again, we can then determine how high up something goes, given that its initial acceleration is 24.5 meters per second, and its acceleration is negative 9.8 meters per second squared. Or in this case, the subtraction sign covers that for me. Then we find out that the pop fly goes about 30.6 meters up in the air. Again, once you do this, you find the math is pretty simple. Plug in for t to figure out how long it takes using v equals v naught minus gt. And there you go. The ball is in the air for 2.5 seconds. And as I said before, some things you can math, some things you have to rationalize. Is gravity ever not affecting the ball? No. So even at the top and the velocity is 0, is the gravity being applied to the ball? Yes. Therefore, at the top of its path, you still have an acceleration of 9.8 meters per second squared downwards. Cool. That is a good example of something that usually confuses people, because you kind of have to use y final 2 different ways to solve different questions. But if you stop and think about what the equations are trying to tell you and what the equations have in them, that's part of the process here, right? Realizing that this is essentially a quadratic formula for y will hopefully infer to you that you have an up and a down motion embedded in the equation. More questions along these same lines, well worth your time if you choose to do them. Let's go 3.17, and I think we'll call it a day after that. This is 3.16, right? Yeah. Cool. Kinematic equations in from integral calculus. Again, I want to stress, if what you're looking at the screen right now makes no sense to you, you don't know what that little fancy looking line is next to the d divided by dt, if you think that's d divided by dt, you need to talk to someone to catch you up on your calculus. I'm not going over the basics of the math because I'm assuming you don't need me to go over the basics extensively. Otherwise, you wouldn't be in the calculus-based physics class. But yeah, you could take integrals of things to go from velocity, acceleration, and stuff like that. Because, as I said before, acceleration, velocity, and displacement are all derivatives of each other, and therefore they're integrals of each other, right? That's just different paths. So there you go. Takes the integral of the velocity, gets the displacement, takes the integral of the acceleration, gets the velocity. Yeah. You can, as I said, I don't care if you just write all the equations down that are useful and not worry about deriving the velocity from the acceleration. Like, it's up to you. Cool. Let's start with 3.17, and then we'll call chapter 3 a day. Motion of a motorboat. So a motorboat is traveling at a constant velocity of 5 meters per second when it starts to accelerate opposite to the motion to arrive at the dock. It starts to slow itself down, right? The acceleration is negative a quarter t meter per second cubed. So its acceleration it's decelerating, 1, because it's negative, and 2, there's a t in the acceleration equation. Interesting. What is the velocity function of the motorboat? That's calculus, right? At what time does the velocity reach 0? So when does the boat stop moving? What is the position function of the motorboat? Useful, you want to make sure you're close to the dock. And what is the displacement of the motorboat from the time it begins to accelerate opposite to the motion to when the velocity is 0? So how far does the boat move before it stops, right? Useful things. You're on a boat. Boats don't really behave all that well usually. So you want to make sure that you don't slam into the dock, or that you don't stop moving well away from the dock and have to start again. And it's super embarrassing. So let's take a look at our equations and try to solve what's going on here. So from the functional form of the acceleration, as shown here, we can solve for the velocity function given the acceleration function. We know that the acceleration function was negative 1/4 t dt, plus, of course, some c1 by definition. So if we integrate that, if you remember how to integrate, you find the velocity function looking something, the velocity function looking something like as shown here, negative 1/8 t squared plus some constant c1. So given that information, we can look at and solve some of the questions here. We know, for example, at t0, we have a velocity of 5 meters per second. So v sub 0, or v of 0, equals 5. And we have the equation now in terms of v of t. And so if t is 0, then the equation equals 5. So we can rearrange to get ourselves a nice pretty little equation as shown here. V of t equals 5 meters per second minus 1/8 t squared. The constant c1 is 5 meters per second. So when we go to part B and we determine the time it takes for the velocity to reach 0, we substitute v sub t for 0 and solve for t, right? So we take that v of t there, replace that with a 0. So 0 equals 5 minus 1/8 t squared, math, and you land at 6.3 seconds. So it takes 6.3 seconds for the boat to decelerate. It's a long time. Hopefully you're not too close to the dock, right? So with that information, what's the position function look like? Well, since to go from acceleration to velocity, we integrated. To go from velocity to displacement, we again integrate. So we take our velocity equation of 5 minus 1/8 t squared, integrate that with respect to t, and we land on, again, I don't want to go over how to do an integral again, because I don't think that's the point of the physics class. But when we go through the integral, we land on displacement is equal to 5t minus 1/24 t cubed. And then taking that equation lands us at a displacement for this deceleration of 21.1 meters. Pretty far away, right? So you got to make sure you are hitting the brakes, if you will, putting the engine reverse on this motorboat pretty quickly. Otherwise, you're going to smash in the dock and not be very happy. And the graphs here show exactly what we're talking about. And yeah, there we go. Good stuff. That is chapter 3. Takeaways from this. 1 was still in pretty basic math, right? You can derive equations out and all that jazz, but the application of the equations are still super easy. You don't need a big fancy calculator to do this stuff necessarily. Second is my reiteration of write everything down, walk through your steps slowly, and that way you're not going to get lost or confused. Have the textbook next to you and write down the equations, right? I grade based on work shown because that's the more important thing here. If you're in a motorboat, you're not going to take the time to mentally calculate the derivative of your given acceleration to see if you can hit the dock, right? That's not the point of the question. The point of the question is to force you to go through these steps slowly, because it gives you 5 different subsections of the question. Go through the steps slowly to see how these equations interact with each other. That's what we're hoping for. With that all being said, thanks for listening. Got any questions? Comment below. Talk to your the people in your class, and take care.